Okay, hello again. In this session, we will talk about the Internet of Things. We will focus on the embedded systems, and the presentation or the videos will be in two parts, matching the slides that I have already uploaded. So we have embedded systems part 1, and we have embedded systems part 2. So we'll start with part 1. Okay, so again, I have said it multiple times in different presentation, but again, imagine a world where every day objects are intelligent, connected, and working together seamlessly. So that's the power of the IoT. But how does it all come together? At the heart of every Internet of Things object devices, there is an embedded system. Think of these as the brains and muscles behind the operations. As our first bullet point explains, embedded systems provide the hardware for Internet of Things devices. These are the microcontrollers, the sensors, and actuators that make up the things in the Internet of Things. They are designed for specific tasks, often with limited resources, yet they are incredibly powerful. But it's not just about collecting data. Our second point emphasizes that the system processing enables data analysis and decision making. These embedded systems are not just passive collectors. They process the information they gather, make decisions, and even trigger actions. This intelligence is crucial for creating truly smart devices. And finally, what ties it all together is the Internet of Things connects these components into a network. So this is the magic of the Internet of Things. It's the network that allows these individual embedded systems to communicate, share data, and work in harmony. So we interact with these characteristics and with embedded systems, often without even realizing it. They are the silent workhorses of our modern world. But what makes them so unique? First, dedicated functionality. Unlike general-purpose computers, embedded systems are designed to perform a specific task. Think of the controller in your microwave or the engine management system in your car. They are built for one job, and they do it well. Next, real-time operation. Many embedded systems need to respond to events within strict time constraints. Imagine an airbag deploying in a car, or a pacemaker regulating a heartbeat. These systems must react instantly and reliably. Then we have resource constraints. Embedded systems often operate with limited resources. This means small size and low weight. Think of tiny sensors in a wearables or drones. Low power. It's essential for battery powered devices like smartphones or remote sensors. Many embedded systems operate in harsh environments, from extreme temperatures in industrial settings to the vibrations of the rocket launch. They must be robust and reliable. In many cases, embedded systems are involved in safety-critical operations. Think of medical devices, aircraft control systems, or nuclear power plants. Failure is not an option. Cost sensitive is another crucial characteristic. For mass product devices, even a small increase in cost can have a significant impact. And finally, reliability. Embedded systems must be dependable and operate constantly over long periods. They are often deployed in a remote or inaccessible locations, making maintenance difficult or impossible. Next slide. So, there is two fundamental concepts in the world of computing: embedded systems and real-time systems. While they often overlap, they are not quite the same. Let's break the key differences. So first, let's talk about the embedded systems. As you can see, the definition here is specialized computer systems designed for specific tasks within a larger device or system. Think of them as dedicated problem solvers found in everything from your washing machine to complex industrial machinery. They have some characteristics like dedicated function. They are optimized for a particular purpose. Resource constraints. They often operate within limited memory, processing power, and energy. Real-time capabilities. Many require timely responses, but not all. Interactivity. They frequently interact with the physical world through sensors and actuators. Examples include smart thermostat, car engine control units, medical devices, and industrial robots. Now let's move on to real-time systems, or RTS. These are systems where the correctness of operation depends on not only on the logical result, but also on the time it's delivered. Timing is everything. There is a couple of key characteristics, which include strict timing requirements. They must meet deadlines to avoid system failure. Predictability. Consistent performance is crucial. Prioritizations. Tasks are often prioritized based on urgency. Hard real-time. Also, real-time systems can be further categorized. So hard real-time, missing deadline is a catastrophic, like in a flight control system. Firm real-time, occasional missed deadline are tolerable but reduce quality, like multimedia streaming. Soft real-time, deadlines are desirable but not critical, like online transaction processing. Examples include anti-lock braking system, medical pacemakers, industrial process control, and many others. As you can see from this Venn diagram, this is the Venn diagram. As you can see from this diagram, there is a significant overlap. Many embedded systems are also real-time systems, but not all. The key differentiator is the strictness of the timing requirement. Whether it's controlling a household appliance or ensuring the safety of an aircraft, embedded and real-time systems are essential components of our technological world. We already explored some of the fundamental aspects of real-time systems. Now, let's delve deeper into some of their more nuanced characteristics. As you can see, this slide highlights 4 key aspects that further define the nature of these critical systems. First, we have event-driven versus time-driven. Real-time systems can operate in 2 primary modes. Event-driven, these systems respond to external events like a sensor detecting a change or a user input. Think of an airbag deploying when a collision occurs. Time-driven. These systems operate based on a predefined schedule or time intervals. For example, A system monitoring engine temperature might take readings every few seconds. Next, reliability or fault tolerance requirement. In many RTS applications, failure is not an option. This is where fault tolerance comes in. A classic example is a triple modular redundancy depicted in the diagram below. In this setup, three identical systems operate in parallel. If one system fails, the other two can continue to operate, ensuring the system remains functional. This is vital in safety-critical applications like aircraft control or medical devices. Another crucial characteristic is predictability. Real-time systems must consistently meet deadlines and perform within specific time frames. This is to ensure reliable operations. Finally, priorities in multi-programmed systems. In systems with multiple tasks, priorities are assigned to ensure the critical tasks are executed on time. This allows the systems to manage resources effectively and meet deadlines even under heavy load. From airspace to healthcare, real-time systems are essential for ensuring safety, reliability, and performance. To truly understand the distinction between real-time system and embedded system, let's look at some real-world examples. This slide categorizes examples into three groups: real-time embedded, real-time but not embedded, embedded but not real-time. First, we have real-time embedded systems. These are systems where both timing is critical and the system is embedded within a larger device. Example includes a nuclear reactor control, where precise timing is crucial for safety. Flight control, ensuring the stability and safety of an aircraft. Basically, any safety critical systems where failure to meet deadlines can have catastrophic consequences. GPS, providing accurate location data in real time. MP3 player and mobile phones. These handle audio and communication tasks with the real-time constraints. Now we have real-time but not embedded. These systems require timely responses, but they are not embedded within a specific piece of hardware in the same way. Examples include stock trading systems, where decisions must be made in milliseconds to capitalize on market fluctuations. Skype, requiring real-time audio and video processing for smooth communication. Pandora and Netflix, streaming services that need to deliver content with minimal delay to avoid buffering. Finally, we have embedded but not real-time systems. These are embedded within devices but do not have strict timing requirement. Examples include home temperature control, sprinkler system, washing machine or refrigerator. In home temperature control, while it's convenient to adjust your thermostat, delays of a few seconds are usually acceptable. In sprinkler system, where precise timing is not critical, in refrigerator or washing machine, the embedded controllers, are included in these appliances, but do not require real-time responses. When discussing real-time systems, it's important to understand the different ways that they can be categorized. Today, in this slide, we are focusing on static systems. This slide outlines the key characteristics of static real-time systems, which are defined by their predictability and predetermined nature. The first crucial point is task arrival times can be predicted. This means the system knows in advance when tasks will need to be executed. This predictability is the cornerstone of static systems. Next, we have static compile time analysis possible. Compile time refers to the stage where the program is being translated into machine code before it's executed. Because task arrival times are known, analysis and scheduling decisions can be made before the system runs. This allows for optimization and efficient resource allocation. This leads to the third point, which is allows good resource usage. Since the system knows when tasks will arrive, it can schedule them in a way that minimizes idle time for processors and other resources. This results in efficient resource utilization. To fully grasp the significance of static systems, it's important to consider the context. Real-time systems where predictability and timely execution are crucial for proper operations. Embedded systems where resources are often limited and efficient scheduling is essential for performance and power consumption. So we explore the static real-time systems where task arrival times are predictable. Now let's turn our attention to the other end of the spectrum, which is dynamic systems. This slide outlines the key characteristics of dynamic real-time systems, which are defined by their unpredictable and adaptable nature. The defining characteristics is arriving times unpredictable. Unlike static systems, dynamic systems deal with tasks that arrive at unpredictable times. This makes them inherently more complex to manage. Because arrival time are unpredictable, static analysis possible only for simple cases. It's difficult to analyze the system's behavior before it runs. Only very simple cases might be amenable to compile time analysis. This leads to the next point. A processor utilization varies dramatically. Most design systems to handle worst case. Due to the unpredictable nature of task arrivals, processor utilization can fluctuate significantly. To ensure the system functions correctly under all conditions, it must be designed to handle worst case scenarios, which leads to periods of low utilization. Finally, must avoid oversimplifying assumptions. This point highlights the need of careful considerations when designing dynamic systems. Oversimplifying simplifying assumptions, such as assuming all tasks are independent when they are likely dependent, can lead to incorrect or inefficient system behavior. For example, assuming all tasks are independent when this is unlikely is potentially problematic simplification. While dynamic systems present unique challenges, they are essential for applications where tasks arrive unpredictably. In this slide, we highlight the key areas where the concept of dynamic systems is crucial. First, real-time systems. In real-time systems, we delve into our various scheduling approaches designed to handle unpredictable workloads. This involves developing algorithms that can adapt to changing conditions and ensure timely execution for critical tasks. Secondly, in operation systems, we explore dynamic scheduling algorithms and resource management techniques. This is essential for efficiently allocating resources and ensuring responsiveness in systems where workload fluctuates. In embedded systems, we address the challenges of resource management in dynamic environment. This is particularly important for devices that operate in unpredictable conditions or interact with the real world. Ultimately, this slide emphasizes the trades-off involved in designing dynamic systems. In this slide, we outline the key characteristics of real-time systems, which are defined by their repetitive nature. The first characteristics, in this slide we highlight a couple of characteristics. The first characteristics is that each task executes repeatedly within a particular period. Because the execution pattern is predictable, this allows some static analysis technique to be used. This periodicity matches characteristics for many real-time problems. Periodic tasks are common in various applications such as industrial control systems or multimedia processing or even network communication. Importantly, it is possible to have tasks with deadlines smaller, equal to, or greater than their period, as explained in these couple of bullet points below. This slide refers to the classification of systems where tasks or processes repeat at regular intervals. And within this, we find two main subcategories, which are single rate and multi-rate. First, we have single rate. This means there is one period in the system. All tasks operate with the same fixed period. This simplicity makes it simple but inflexible. While easy to implement, it lacks flexibility if tasks have different timing requirements. This approach is used in implementing a lot of wireless sensors networks. This highlights a specific application area where a single rate periodic system are commonly used. Next, we have the multi-rate periodic system. This means the system has multiple periods. Tasks can have different periods. However, it's crucial that these periods should be harmonics to simplify system design. This means the periods should be harmonically related, like one period being a multiple of another to simplify scheduling and avoid conflicts. As you can see, we have explored at the beginning, some period. We have explored periodic systems with their predictable cycles. In this slide, as you can see, a periodic is not only term used. These types of tasks are also described as, sporadic, asynchronous, or reactive. This highlights the fact that these tasks occur at irregular intervals, are not synchronized with a clock, and respond to external events. This unpredictability creates a dynamic situation. Periodic tasks introduce variability into the system. This contrasts with the static or periodic systems where behavior is more predictable. As we can see, a periodic task introduces unpredictability and a variability into the system, making it dynamic. However, bounded arrival time time intervals are easier to handle. Specifically, if there is known upper limit on how frequently a periodic task can arrive, it's easier to design systems that can handle them. This is because you can allocate resources based on the maximum possible arrival time. Conversely, unbounded arrival time intervals are impossible to handle with resource-constrained systems. At this point, as this point clarifies, if there is no limit on how frequently a periodic tasks can arrive, it's impossible to guarantee that system will be able to handle them all, especially in resource-constrained systems. This is because you cannot allocate infinite resources to handle an infinite number of potential arrivals. This slide outlines key aspects of control systems, focusing on how humans interact with them. First, we have man-machine interface. This is how humans interact with the technology. In Internet of Things, an embedded system, this can range from a simple LED display to complex web interface or even a voice control system. It's all about making technology accessible and user-friendly. Next, we have instrumentation interface. This is crucial in connecting the digital world to the physical world. Sensors measure physical parameters like temperature, pressure, or light, and convert them into digital signals. Actuators take digital commands and translate them into physical actions, like turning a motor or opening a valve. Then we have hard real-time. This means the system's deadlines are critical. Missing a deadline can lead to catastrophic consequences. The example given is the fuel injection in a car. If the fuel is not injected at the precise moment, the engine won't run efficiently or could be damaged. Finally, we have deadlines determined by control object. The timing requirements of the systems are dictated by the physical process being controlled. For example, an ATM has less timing requirement than a fuel injection system. The controlled object sets the pace. This diagram illustrates a basic one sensor, one actuator control system. This diagram illustrates a basic one sensor, one actuator control system, a fundamental concepts in engineering. Let's walk through the components. We start with the reference input RT. This is the desired value or set point, like the temperature you want your thermostat to maintain. It's an analog signal. This signal is converted to a digital value RK by the AD converter, by this AD converter, which stands for analog to the digital. Simultaneously, this sensor measures the actual output, which is Y of t, which is also an analog signal. This measured value is also converted to a digital value YK. So this is analog to digital, converts the measured value of that came from the sensor to a digital value yk by another AD converter. The heart of the system is the control law computation block. Here the system compares the desired value rk with the measured value yk and calculates the necessary control action uk. This digital control action UK is then converted back to analog, analog signal called UT or U of T by the DA converter, digital to analog converter, which stands for digital to analog converter. The analog signal U of T drives the actuator, which in turn affects the plant or the system being controlled The plant is influenced by the actuator outside effects, which are disturbance or factors that can affect the system output. The components within the dashboard, red box, represent the control system itself. This slide presents the pseudocode for a typical control system, illustrating the steps involved in its operation. Let's break down the code. The system starts by setting a timer to interrupt periodically with period T. This timer is crucial for ensuring the system operates at regular intervals. The core of the control loop is executed at each timer interrupt. First, the system performs an analog to digital conversion to get Y. This converts the sensor's analog reading into a digital value that the system can process. Next, the system computes the control output U. This is where the control algorithm comes into play, calculating the necessary adjustment based on the measured value and the desired set point. Finally, the system outputs U and performs digital to analog conversion. This converts the digital control output back into analog signal that can be used to drive actuators. The loop then repeats at the next timer interrupt, continuously adjusting the system. As noted, T is called the sampling period. This is the key design choice as it determines how frequently the system updates its output. The typical range for T is from seconds to milliseconds depending on the application's requirements. This pseudocode provides a clear overview of how control system operates, highlighting the importance of periodic sampling and the conversion between analog and digital signals. We have spoken about sensors and actuators in previous class, so please refer to the previous lectures. Let's talk about communication. This slide outlines the fundamental aspects of communication in connected systems. First, communication connects devices with each other and the cloud. This enables devices to share data, coordinate actions, and access remote resources. Communication can be broadly categorized in two types: wireline, which uses physical cable copper wires like optical fibers, and wireless, which uses radio frequency RF or infrared RR signals. Let's look at some of the popular RF-based communication solutions. The first one is often used in low power wireless sensor networks. IEEE 802.11 which is more commonly known as Wi-Fi for high-speed wireless internet access. Bluetooth is for short range communication between devices. NFC used for short range contactless communication like in RFID tags. In this slide showcase the Raspberry Pi ability to interact with physical world through its I/O pins. As you can see in the image, we have a Raspberry Pi connected to a breadboard using a ribbon cable. This setup allows us to experiment with various electronic components. The ribbon cable connects the Raspberry Pi GPIO, which stands for General Purpose Input and Input-Output pins, to the breadboard, providing convenient way to connect sensors, actuators, and other devices. In this example, we have a lid connected to the breadboard, demonstrating a simple output function. We can control the lid's state using the Raspberry Pi GPIO pins. The Raspberry Pi GPIO pins can be configured as either inputs or outputs, allowing for a wide range of applications. We can connect sensors to read data from the environment, or actuators to control external devices. GPIO pins like I said, refers to the pins on a microcontroller or single board computer that can be programmed to interact with outside world. As you can see, you can program the pins, making them incredibly versatile. Specifically, you can use them as input to a pin from a sensor or another computer or device. This allows you to connect various sensors like motion sensors, temperature sensors, enabling your system to gather data from its environment. You can also use them as an output, so you can output from a pin various actions. This includes turning on a lid, operating an actuator like a motor, or even sending a signal or data to another device. This allows your system to control external components. Furthermore, when you have a networked Raspberry Pi, you can achieve even more. This enables remote control attached physical devices and receiving data from other devices, opening up possibilities for remote monitoring and control applications. I will skip this slide. I will talk a little bit about the bus architecture. This slide illustrates the key components of a system bus and the two primary methods of the data transmission, which are serial and parallel. So let's start with the system bus. This is the backbone of a computer, enabling communication between the CPU and memory, between CPU, memory, and input and output devices. The system bus consists of three main components: the address bus, which carries the memory addresses that the CPU wants to access; the data bus, which carries the actual data being transferred; the control bus, which carries control signals that coordinate the activities of the different components. Now, let's look at the two primary methods of data transmission, serial and parallel. In serial communication transmits data one bit at a time over a single communication line. Parallel communication transmits multiple bits at the same time over multiple communication lines. As you can see, serial communication is like a single lane road, while parallel communication is like multi-lane highway. Now let's go back again to the breadboard and see how it works. So a breadboard is a solderless device used to build and test electronic circuits. The key to understanding how a breadboard works lies in its internal metal strips underlying the holes. These strips act as jumper wires connecting components. These strips are arranged to connect specific rows, columns of holes, creating electrical pathways. Electrical components, leads, and wires are inserted into the holes, making contact with the internal metal strips. This allows wire to connect electric components leads, forming a circuit. In essence, building circuits with a breadboard is simple as sticking component and wires into the holes. This makes it easy to experiment with different circuit configurations without the needing for soldering. As you can see in this image, these pins are located along the edge of the Raspberry Pi board. The GPIO pins serve as the physical interface between the Pi and the outside world. They provide a way to connect sensors and actuators and other electronic components. Essentially, these pins can be viewed as switches. They can act as that you can turn on or off input, allowing you to read signals from external devices, or they can act as the Pi can turn on and off output, allowing the Raspberry Pi to control external devices. This flexibility makes the Raspberry Pi a powerful tool for building a wide range of projects, from simple LED circuit to complex IoT applications. This particular image shows the GPIO pins in Raspberry Pi, I think 2. Yeah, we can see Raspberry Pi 2 model P, but the concept is the same across Raspberry Pi models. As you can see, there are 40 pins on the board in total. Out of these, 26 are GPIO pins that you can use for your projects. The remaining pins are others are power or ground pins, providing the necessary power and grounding for your circuit. This diagram shows the specific layout of the GPIO pins on the Raspberry Pi A+, B+, and Raspberry Pi 2. The colored coded ligand, as we can see here, helps you identify the function of each pin. Yellow represents GPIO pin, black represents the ground pins, orange represents 3.3 volt power pins, and red represent 5 volt power pins. It's worth nothing that the IDEE form pins are for advanced use only, and typically not used in beginner projects. Understanding this pin layout is crucial for connecting sensors, actuators, and other components to your Raspberry Pi. This particular pin layout is specific to the Raspberry Pi A+, B+, and Raspberry Pi 2 models, but the general concept of the GPI pin applies to all Raspberry Pi models. Okay, so we have reached the end of Internet of Things Embedded Systems Part 2. I will be posting another video for Internet of Things Part 2. Thank you so much for listening.